So the second video in this series is going to be calorimetry. This is a very easy technique that we use in the chemistry lab to determine the heat that's been transferred in a chemical or physical process. Okay? So this is what I said in there. What we measure is the amount of heat that's been transferred. Okay? We have to use an instrument, they call it calibrate. Basically, in the chemistry lab, we're going to assume the calorimeter is perfectly insulated and it does not absorb any heat. So all of the changes that we observe are due to the transfer of heat from the system to the surroundings or from the surroundings to the system. Unfortunately, in real life, that's not true. It's a good approximation for a general chemistry lab, but when you use that like in industry, you do calibrate the calorimeter, meaning you know how much heat the calorimeter is going to absorb, because it will absorb a little bit, okay? But basically with the calorimeter, what you measure is a change in temperature that then you're going to use to calculate the amount of heat. And you have an idea because we saw an equation in the previous video, so you suspect what's going on in here. We've already talked about the system and the surroundings. Let me make sure that we get this straight. The system is the substance that's undergoing a chemical or physical change. It can be, like I said, a piece of metal that is very hot and you put it in a beaker with water. In this case, the piece of metal will be the system. Or it can be a chemical reaction. Let's say that you have hydrochloric acid and sodium hydroxide forming sodium chloride and water, that those chemicals are going to be the system. Now the surroundings is everything that surrounds them with, you have to put a limit in there, okay? But we'll get to that in a second. What is surrounding the piece of metal? The water. So that is surroundings in here. The metal will be the system. We said the chemical reaction is the system, but the chemical reaction is going to take place maybe in a test tube, right? It's going to be an aqueous solution. So that solution will be surroundings. Now, like I said, you need to put a limit on how far you go with the surroundings, because you're saying, okay, the water in the test tube surrounds the chemical reaction. Okay. So the lab surrounds the test tube. Yeah. And the building surrounds the lab. And the campus surrounds the building. And you could go on and on and on and on. I always tell the students, when you do the chemical reaction, you can feel with your fingertips any temperature change in the test tube, but it's not going to change the temperature of the lab. Not enough heat is produced. So we only consider surroundings to the part that actually absorbs heat. Okay, wherever you can measure the heat that's been absorbed. The test tube, you can measure the temperature, the change in temperature with a thermometer, you call it surroundings. The lab is not going to change temperature, so we do not consider the room part of the surroundings. Okay, so it's just being reasonable, because you could go on and on all the way to the universe if you want to pull it out. So we say calorimeter is an instrument that you use to measure the amount of heat. Basically, it's an insulated thing with a thermometer. Usually you have a solution, an aqueous solution in there. So you put whatever your system is, the piece of metal, or you have your chemical reaction in there. If the process, because it doesn't have to be a chemical reaction, is exothermic, meaning it releases heat, the temperature of the water surrounding it is going to increase. The heat comes out of your chemical reaction or comes out of the hard piece of metal, and you read the temperature before and after, and you see the temperature went up. What if what I put is a block of ice, or I put a reaction like the cold pack, something that's going to absorb heat? If it's endothermic, it's bringing the heat to the inside. Where does it take the heat from? From the surroundings. So the surroundings have a drop in temperature. You measure the temperature before and after, and you can see that heat has been transferred from the system to the surroundings. So it's a very easy system, and basically all you're going to be doing is reading temperature before and after the process, and from there you're going to be doing calculations. So you have an example in here. You have a hot piece of metal, you put in cold water. When you first read the temperature, that's going to be your initial temperature, before you put the metal. Then you put the metal and the heat comes out of the hot metal, right? The water warms up. So you read now the final temperature after. You know the temperature of the metal is going to decrease because it cools off in the water. The temperature of the water is going to increase until you reach a chemical equilibrium. So we can calculate the heat that was lost by the metal and the heat that was gained by the water by the equation that we saw before. Now, the calorimeter is insulated, so there shouldn't be any loss of heat to the outside. You can see the overall change of heat is zero. All of the heat from the metal is going to go to the water, none is going to be lost. So that means that the value of the heat of the metal is going to be the same than the heat of the water, but they have a different sign. Why? Because the metal is losing heat, that's why it's negative. The water is gaining heat, and it's positive. Okay? So equal in magnitude, but opposite signs. I told you in thermochemistry, the signs are going to be very, very important because they're going to tell you in which direction the heat is moving or the energy is moving. That's why you want to be very careful. And when you calculate heat, always use final temperature minus initial temperature, because then you'll have the correct signs all the time. If you give the answer with the wrong sign, it's going to mean something completely different, and I'm afraid that your answer is probably going to be considered wrong. So you have an example. They give you a piece of rebar, that's a piece of metal using concrete and all that. They give you the mass of the rebar. You put into this amount of water, and they tell you the water at this temperature. So you give it a bit of time until there's equilibrium, and now the temperature of the water is 42.7. It went up a lot. So they want to know what is the initial temperature of the piece of metal. And they tell you assume that the specific heat of the steel is the same for iron, and you will have a table in there, and then all the energy transfers between the metal and the water. There's no heat loss because they're doing it in a calorimeter. Okay, so if there is no heat loss, you can say that the heat lost by the piece of metal is going to equal the heat gained by the water. Now we can calculate the heat of the metal, but you can say this is the heat from the metal is negative because it's been lost, equals the heat of the water, and we are going to expand it to put final temperature minus initial temperature in here. And now you're going to go to the problem and start putting. Now there's one thing that drives students crazy, because they said they give me the final temperature for the water, but they didn't give me the final temperature for the metal. They said the final temperature for the water was 42.7. And I had a student stop and say, but I don't have the final temperature of the metal, so I cannot do anything. Remember, when you put something hot in cold water, it's going to eventually reach equilibrium. You don't read the temperature until it has reached equilibrium, so the final temperature of the metal is going to be the same thing as the final temperature of the water. Okay? Keep that in mind. It seems common sense, but it happens over and over and over. Students in an exam raise the hand. You didn't give me the final temperature of the water. Yes, it is. You didn't give it to me. Look it up. Just warn you, but just know that's my favorite thing to do. Warn you about the mistakes that the students tend to do over and over and over. So we start replacing, and you say, okay, this is the heat, specific heat of the metal that we look it up in the table. That's the mass of the metal. That's the final temperature. We don't know the initial. That's what they're asking us. Specific heat of the water, again, you look it up. Let me just write down this from the table. Specific heat of the water you get from the table too. How about the mass of the water? Well, you know the density of water is 1 gram per ml. So 425 milliliters is going to be 425 grams. The final temperature of the water was given to you, not explicitly, but you know it's the same than the final temperature of the metal, and they give you the initial temperature. So you can have an equation like that, there is one unknown in there. You can isolate it and tell you the initial temperature of the metal was 248 degrees Celsius. This, by the way, is probably the most complicated calculation you're going to find in calorimeter. Most of the time, they're going to give you both the initial and the final temperature for both, and you're going to have to either calculate specific heat or mass, usually of the metal in this case, which means the calculations are going to be a little bit simpler. But still, even this one, don't try immediately to isolate this. I tell my students, calculate this is going to be a number. Okay? And calculate this is going to be another number, and all of a sudden you have 42.7 y, that's minus y initial temperature equals x. Now y is a number, so you can isolate the temperature much easier. Just do any calculation you can to simplify. But we'll do problems. Like I said, if you can do this one, you can do any. Because this is the one that mathematically is to be more complex. All of the other examples, the math is going to be much, much simpler. Okay? But in every single case, you have actually 8 variables, because you have specific heat of 2 substances, mass of 2 substances, initial temperature, final temperature of 2 substances. You're going to have 8 variables. They're going to give you 7 and ask you for the 8th. And it's just a matter of algebra to calculate the value of the 8th. Okay? Now, sometimes we use calorimetry to determine the heat involved in a chemical reaction. Okay? But it's still the same principle. Okay? We are going to assume again that the calorimeter does not absorb any heat or something like that. So you have the heat that is produced by the reaction, we call it heat of reaction, plus the heat that the system is going to absorb or lose depending whether the reaction is endothermical or exothermical, we call it heat of solution. And once again, because it's perfectly isolated, we're going to assume that the overall change of heat is 0, or, and this is exactly the same thing we did before, the heat of the reaction is going to be equal to minus the heat of the solution, meaning they have the same magnitude but opposite signs. If the reaction is giving off heat, is losing heat, that means the solution is going to absorb the heat. When the reaction is absorbing heat, the solution is losing heat. So this is a case where plus or minus, this is generic, okay? In some equations it would be minus heat of reaction and positive heat of solution. It depends on the particular reaction. But this is such a simple type of calculation that we just did with the metal. We are going to have to make a few assumptions because we are not going to be able to, we don't know the density of the particular solution that you have. They're all going to be diluted solutions, and we're going to say, oh, we're going to assume the density is that of water. We're going to assume the specific heat is the heat of water because they're very dilute solutions. Okay? But we can solve this equation just the same way that we did the previous one. And this is the equation that I gave you before. But they give you the volume of hydrochloric acid, give you concentration. They give you the volume of sodium hydroxide. They're both at 22 degrees. You mix them, and now the calorimeter, the temperature goes up. Anytime you have an acid react with a base, it produces heat. So they want to know how much heat. Okay, if you could, and you can't, okay? But that's why I said we make some assumptions in there. But if you could mix the two solutions so quickly that there's no reaction yet, you realize that what you have is 100 milliliters of your mixture. You have 50 milliliters of one, 50 of the other one, so you end up with 100 milliliters of your mixture at 22 degrees. And then, like I said, they react and the temperature goes up. We said that the value of the heat is going to be the same reaction solution with opposite signs. So we cannot measure the heat of the reaction, but we can measure the heat of the solution because we did in the calorimeter. We measure the temperature, mix the solutions, measure the temperature again. So the specific heat of solution, we say we're going to approximate and say that's a diluted solution let's just say it's the specific heat of the water. Okay? The mass of the solution, when we had 100 milliliters and mass is in grams, we are going to assume, again, this is the Lewis solution, that the density is 1 gram per ml, so we have 100 grams of solution. Final temperature minus initial temperature, that gives you the heat of the solution. Again, you put final minus initial, the heat of solution is positive. And you know the solution went up in temperature. So once again, the signs make sense. Okay? If you reverse the two temperatures, you're going to get a negative heat of solution, and that doesn't make any sense because you know the solution went up in temperature. Now, if you had the heat of solution, you know the heat of reaction is the same number with a negative sign. So this is the heat that's released by the reaction, and it's negative because it's an exothermic reaction. The heat is being lost by the reaction. It's gained by the solution, but it's lost by the reaction. Okay? But this is the amount of heat, kilojoules, because it's 10 to the 3 joules. If you want to answer 2.9 10 to the 3 joules, that'll be fine. But it's very important you have the correct sign because the heat is coming out of the reaction. And again, you get the right sign if originally you put final temperature minus initial temperature. I know I'm going over the same thing over and over and over, but this is something that doesn't seem to matter how many times I explain it. There's always a large number of students who get it wrong. I want to mention the bomb calorimeter. Is used for reactions that yield either a lot of heat or gaseous products, and it's used a lot like to determine the calories in food. Okay? Now, if you're going to produce gaseous solution, something like that, obviously you can have a flame here in here. So you have your sample put in here, and you actually use electricity. You have some electrodes, and you're going to combust, or you're going to add the heat by using electricity. Okay? But when the sample of food heats up, this is in a isolated, they call it the bomb, but it's a calorimeter. You read the temperature before and after. Obviously, when you burn that food in there, that's going to heat up the water. So you have temperature before and after, and you can calculate how much heat was released when you burn that. We used to do it in the lab uses, simpler thing, but we have a container of water, and we read initial temperature, then we have a Dorito, and we burn it, and then we read the final temperature. Now, some of the heat was obviously lost because this is not a calorimeter. Some of the heat could come from the flame we used for the Dorito. It wasn't perfect, but it was amazing because we calculated how many calories per serving, and we always come up with a number unbelievably close to what is said on the bag of Doritos. It was a really fun lab to do. But like I said, this is how they calculate the energy content of food. And you look at the nutrition facts, and one other things, they're going to tell you how many calories. Now remember, these are kilocalories per kc, but that's how they do it with the bomb calorimeter, okay? As far as the rest of the world uses kilojoules, I'm planning on a trip to Spain very soon. I can't wait to look at the packaging or something and see if they really use joules or not. But we're in the US, all of your labels are going to be in calories. Just remember, these are not regular calories, okay? These are food calories that equals 1,000 regular calories. So I do have a worksheet with calorimetry problems. They're not difficult at all, but there's variation. They may ask you what is the mass of your system, or what is the specific heat of the system, or what is the initial temperature, or what is the final temperature. There's all sorts of different variations in these problems. So I do have a worksheet that you can practice to make sure that you do this right. It's all the same principle. It's all the same equation. Okay? The heat gain or loss by the system has to match the heat gain or loss by the surroundings, just opposite signs. They're going to give you everything but one variable, simple algebra. But if you want to practice, go to a video description, go to Wysant, make an appointment, and I will be glad to send you a copy of the worksheet and maybe even go over the problem with you. Okay? Once again, any problem that you do online with me does not get graded, it gets corrected, it gets explained, but then when you do it in class or in an exam, you get a good grade and everybody's happy.